The deadline here. My name is Ivancich. I live in Ann Arbor, Michigan. And among other things, one thing I do is I teach Ruby. And so I have learnruby.com where I offer Ruby training. And this talk is about ropes, which is something that I just recently discovered as a result of a certain programming contest, which I'll discuss very briefly here. And basically, we'll see that a rope is an alternative to strings. This is very much going to be a data structures talk, so something that you might have seen before, but it has some particular aspects that are focused on Ruby here. All right, so I'll cover the background of how I discovered ropes. I'll discuss the rope data structure, and so you can see how it will actually work. We'll then discuss Ruby implementation. You'll see some actual code at that point, next step and challenges, and finally, the closing here. All right? The background. How many of you visit the Ruby quiz regularly or even participate in the Ruby quiz regularly? I really like it quite a bit because as long as I've been doing Ruby, which has only been like a year and a half or thereabouts, maybe 2 years, I'd find that I'm still learning new things by comparing my solutions to various quiz questions with those others who've submitted their answers to the same quiz. So it's a very great educational experience, and I highly recommend it. And if you go back to July, the administrator of the Ruby quiz, his name is James Edward Gray II, who couldn't be here at RubyConf this year because his sister is turning 18 this very weekend. He posted a note, basically said the Ruby quiz would be on hiatus because he'd be participating in the International Conference on Functional Programming's, their contest, their programming contest, which they hold every year. Let me give you a brief sense of what the contest was. Did anybody participate in this contest by any chance? And which language did you use? You did it with James, okay. Basically, this is quite a programming contest. I hadn't heard of it before. I've never seen one that was quite as detailed and as complex as this particular one. You had 72 hours to write software to do something, and every year that something is going to change. And this year, the backstory was that an alien crash landed on Earth. He was about to die because his DNA was not well adapted to the Earth environment, and you had to, through some DNA encoding, give him some extra DNA that would allow him to morph and survive in the Earth environment. All right? And the process was basically this. You're provided with his initial DNA, and the DNA would be transcribed according to a spec to RNA, and from there it would go according to another spec into a source PNG image. All right? That image was supposed to represent the actual life form. And you were given the specs for how the DNA went to RNA and the RNA went to the source image, and you had to provide the code which did all of that. So you got the things in green there. You had to provide the things that are in red. Okay? Now the goal was to come up with a DNA prefix to put ahead of the DNA that would change the way the DNA was processed, giving you a different RNA and giving you a different image at the very end. All right? Also given the target image. And basically, you were evaluated based on the size of your prefix and how close your target image was to the desired target image. And there was some sort of difference computed there. And there was a calculation based on those two parameters. And that, though, was not enough because the DNA was relatively complex, and you had to, or many of the people who did well on the quiz, or the contest, I should say, developed various tools in their languages of choice to help them disassemble and analyze the DNA, help them gain a better understanding of how the DNA worked, which they could then channel into coming up with the best possible prefix that they could in that amount of time. And here are the source and target images that they were given. Okay? You can see the alien on the left there. That's his original form. And he wanted to morph in something on the right, which is more cow-like, I guess. And the actual image processing was relatively complex in and of itself. It's all vector-based. If you look at the arms of the windmill, they're rotated ever so slightly. Okay? There's an underlying vector graphics engine behind all of this. All in the DNA and so forth. And the puzzle was relatively complex. It was 22 pages of spec that you had to interpret and write programs to process. And this gives you a small sample of what the spec looked like. Now, how does it relate to ropes? Well, on one of the last pages of the spec, there was that little sentence highlighted in red down there. It says, it seems particularly important to ensure that, that performing skips and appending uncoded references, these are in these long DNA sequences, perform better than in linear time. All right? Now, if you use a string and you do append strings, you can probably imagine that's not going to be linear. That's not going to be better than linear time. It will be linear time. And the same thing is true with arrays. Skipping is actually constant time, as you can probably imagine. But that was part of the challenge, was to come up with a data structure that would handle that well. If you think that you might want to use linked lists, that would certainly give you the requisite time for appending, but skipping will still be linear. All right? And these are long DNA sequences here that you might be using strings or linked lists or something like that to store. Some of the contest participants, by the way, I was not a participant. I just discovered it. And when I saw the scale of the contest, I wasn't prepared to devote the next 72 hours of my life to trying to do all of that. So I kind of was a lurker and observed this whole process. But those who were using C++ simply dropped in a rope library, and they were on their way. They had solved that problem with basically one single step. Okay? People who were using, I think Haskell, had an equally powerful data structure that dropped in themselves. I had never heard of ropes, so I started looking into them, and that kind of became my area of interest for the next little bit. Okay? And there's been quite a bit of recent interest in ropes, okay, in the Ruby community. First there was the programming contest, and then I started playing and building a library up, and I submitted a proposal for this very talk that you're attending right now. And then there was a discussion, not a huge discussion, in late August, followed by James Edward Gray II, thought that ropes were kind of cool and developed a whole Ruby quiz surrounding them. So I'm part of a number of people now who've been working on ropes within Ruby. And I haven't checked out all the other implementations, but there might be something useful there as well that you might want to look into also. Let's now discuss how ropes actually work. And the basic idea is that the data is broken down into smaller blocks. All right, you can maybe configure the size of the blocks. And those blocks are organized in terms of a binary tree. All right, so there's a nice little example of how you might encode the string of the letters from A through T as part of a rope. Nothing too complex. You've probably all seen binary trees and things like that, encoded them so far, coded them in the past on your own. I'm using a block size here of 4, but you can imagine in the real world they would be somewhat larger to be more efficient still. All right? Now, how does append work when you're dealing with ropes? Well, imagine you have, when you're dealing with strings. Look at strings first, and then we'll look at how ropes compare to strings. But we're going to append onto the end of S1 another string. Okay? How would that work? Well, you first have to allocate a data block to hold the new combined larger string. You copy the data from one string into the first part of the block, and from the other string into the other part of the block. And then there's a little bit of finishing work to do where you allocate the string maybe, or maybe you did that beforehand, fix a few pointers, and you're basically done. But that's going to basically be linear time to append one string onto another string. How would it work with ropes? All right, again, we have 2 small ropes here as our example case. And the first step is basically you're done. You allocate the rope, fix a few pointers up, allocate maybe an interior node there, and you're done. But it's constant time. All right? So appending is relatively quick when you're using ropes as opposed to strings. Furthermore, a lot of the data there is shared, all right? Meaning that you're consuming less memory overall when you're using ropes than you would be with strings because there's less duplication going on there, okay? And these are relatively small trees, but you can imagine that if these trees were much larger, many levels deep, that quite a bit of information would be shared between the various ropes there. How would a slice work, or as the rest of the world knows it, a substring, all right? Well, there's a much larger rope there that has maybe 3 levels of interior nodes, and we want to get the 16 characters starting at the 6th and ending at the 21st, I guess it would be, all right, from the G all the way through the V. Okay? Basically, you could create a tree and share most of the interior nodes. Maybe you have to make your own nodes at the 2 ends to pull out just the correct number of characters you want, but the interior part can actually be shared. And if you want to see what the resulting tree looks like, I can fade out the other stuff, and you can see that basically everything in red is shared, and everything that was in yellow is created just for this slice operation. Okay? And that's going to be order of log n, as you would imagine. All right? And one of the cool things you can do with ropes is you can map it onto a file. All right? So you have some huge file, and we're going to map a rope onto that, which means we're going to put a tree right on top of it, all right, where each leaf node is referring to some portion of that file. And let's do some quick back-of-the-envelope calculations here. If that file were 5 megabytes, and we decided that our rope data block should be a 1 kilobyte in size, then we would need over 5,000 data blocks, all right, and over 5,000 interior nodes, and there'd be about 12 levels of interior nodes there. Okay? Certainly that's not something we want to create as soon as we open up the file. That would be a lot of stuff to actually create at that first moment when we look at the file. And it's especially true if we only wanted to look at scattered portions of the file. So if you see there's parts of the file that are now in green, but read a header, we would use the header to find out that there's something interesting deeper into the file, which we would then read, and find out something else deeper into the file, which we'd read again. And to have created that whole tree, just to look at those few parts of the file would have been relatively wasteful. Okay? So, we don't want to build the entire tree initially, and we certainly don't want to load the whole file into memory initially. So what are we going to do? We're going to do things lazily. All right? This kind of brings up some themes that were brought up in Jim Weirich's talk earlier today. So we are only going to build the tree nodes that we need to, and we'll only read in portions of the file that we need to. All right? So how might we implement this in Ruby? And this is where I think things get more interesting. And here's a little bit of a class diagram to kind of show you the various elements here. But there is a rope class, which holds all the top-level information about a rope. The most important thing is probably that root node at the very top. There's the idea of the interior node, which is the one that has the left pointer and the right pointer, which we'll be using until we get down to the leaves. Then we have a leaf node, which serves as actually a superclass. This is going to be an abstract class. We won't actually ever instantiate it, but it holds the basic functionality for the leaf nodes, which will be inherited by some other kinds of leaf nodes, like a string node if we're mapping a rope onto a string, a partial string node if we only want part of a larger string. We don't want to have to copy that part. We'll just say, here's the entire string, but we're only looking at these characters here in the middle someplace. And a third kind of leaf node, which is a file block node, which maintains information about the file it's referencing, and we will only then read the data from the file when someone tries to access that particular data. All right? And there's one more class involved here, which is the lazy node. This is the one that's going to allow us to do things in a very lazy fashion. And basically, it represents a not yet constituted subtree. Okay? Holds enough data to build that subtree when we actually do need to resolve it. But we're happy to leave it as a lazy node until we actually need the data that sits down below there someplace. So let's actually go through the process and see how that actually works. So we have a string from which we're going to be building a rope. We have a rope that has an interior node and it has two lazy nodes down beneath it. And it turns out that it made the code a lot simpler if that the only other class that had to know about lazy nodes was the interior node class. So lazy node never appears at the direct top. We always have at least an interior node above any lazy nodes. All right? And now we want accessing data within the rope, and we go down the left-hand side of that interior node. The lazy node gets obliterated, and we recreate another interior node and some lazy nodes to represent the further level of the tree there. We go down the right-hand channel this time. We get another interior node and two more lazy nodes. And let's say this is now, we're at the leaf level, and the lazy node will now turn into a partial string node. It refers to a certain part of the string we use to initialize the rope. And if we read the other part of the other side of that interior node as well, we'll get another partial string node. Okay? But here's the interesting thing, at least I think. Where was the information kept about that string that was being referred to until we got down to be able to create those partial string nodes? Where did that information actually reside? Okay? And Ruby provides a really elegant way to handle this kind of situation there, because basically the lazy nodes have inside them closures, or you might call them blocks. And the blocks have the code needed to create the appropriate kind of leaf node at the appropriate time down the road, and because these are closures and not just code, that maintains the reference to the initial string all along the way until we actually get to the point where we actually need that information to create the ultimate leaf node there. And at this point, we'll look at a little bit of code here just to show you how simple it actually is to do using Ruby. All right? Here's the interior node class, which is statically within the rope class. And it's not the whole interior node class, but it's much of it. And you can see there's an initialize method, which is given a left and a right, which we then store. We do some size computations right up the front. And then rather than accessing the left or the right node directly, we access them through some private methods. The private method for left node will check to see whether or not the left node is a lazy node. And if it is, it'll resolve it first and store that in the instance variable and then return that. Okay? So the first time through, it resolves the lazy node, and from that point forward, all the data is actually there. And the same thing basically occurs on the right-hand side. Okay? So that's how the interior node works. Now let's take a look and see how the lazy node works. All right? When we initialize the lazy node, we supply a leaf node builder, which is actually the closure, the block of data which knows how to create leaf nodes for that kind of tree, based on whether we created it from a string, a file, or something else. We also know the start and the size of that particular block, and the block size that we actually want to use. And it just stores all those in instance variables. Then when we get to the point we want to resolve that lazy node, we'll check to see whether the size is less than or equal to the block size. If it is, we're ready to create a leaf. And we'll actually call the code in that leaf node builder. Again, it's a block or a closure. And we pass it the start and the size, and it knows how to build that particular kind of leaf node. All right? If, on the other hand, we're not ready yet to create a leaf node, we'll create another interior node. All right? Compute split decides how to divide the string data between the left and the right-hand side. It tries to be optimal in various ways. It returns back a hash. It tells where the start and the size of the left side is, and the start and the size of the right side is. We use that information to create two lazy nodes, one for the left, one for the right, and we pass that leaf node builder that we had down to the next level. So we're maintaining it between all the various levels. And the last step is to create an interior node from those two lazy nodes. All right? So relatively easy in Ruby to make it lazy and make it nice and efficient. Now the rope class, again, this is just a small excerpt from the rope class, but when we create a rope from a string, all right, we somehow have to tell it that we're going to be using these partial string nodes to create the leaves. And again, that's passed to new helper as a block. So you'll see that we call new helper with two parameters plus a block, which has the information necessary to create the leaf nodes. All right. New helper just creates a lazy node from that information there, passing that block as the first parameter to the initialize method of leaf node, a lazy node rather. Okay. Now, when I created this, I was actually looking at the SGI library in C++ to see what kind of methods they provided within their rope class. And they, of course, provided traditional iterators. All right? If you've done Java coding or C++ coding, you probably use these. But basically, when you want to sequence through some large piece of data, some collection of data, you create an iterator. The iterator has to keep track of where within that large collection of data you currently are. All right? So you say, what's the next character, and it gives it to you, and then it jumps ahead to the next one. And when I was thinking of it in terms of iterators, I was thinking, man, I have to keep basically a little stack here of where in the tree I am, all those intervening levels between the root and the leaf node, so that when someone asks for the next character, I can then move my way up and down through the tree to get every single character. I was thinking that's going to be a pain to code, but of course I can do it. But I wasn't thinking in the Ruby way when I was thinking in those terms, because in Ruby, things are flipped, all right? We don't create an iterator and then use the iterator. We instead create the code which the iterator uses and pass that to the iterator as a block. And once you do that flip, things kind of melt away, the complexity melts away very nicely, and it becomes almost trivial. Let's take a look here. So there's the leaf node and the interior node, and we're looking at the each care methods in both of those. All right? For a leaf node, the each care method simply has to sequence through the characters in that leaf node, and that's all it has to do. It can ignore the rest of the rope, all the other nodes that are out there. Okay? Retrieve the data, and in case retrieving the data is an expensive operation, I store it in a local variable, and I simply use another little block, the each block right there, to go through all the data and return each character and yield whatever the block was that was passed to it, yield to it, or call it, I should say. Okay? And for the interior node, it's equally simple now. I simply have to recurse and do an each care on the left-hand side, and when that's done, I do an each care on the right-hand side, and again, I'm done. So the block comes into each care, and basically, these two methods here handle all of the complexity of iterating through a rope. Okay? And once you have an each care, you can do an each line relatively easily, way at the top level, at the rope level. Okay? So the each line method simply creates a variable to hold the current line that it's looking at, uses the each care to pull out each character and appending it to the end of the current line. And if we ever reach the end of line separator, we then call the block that was passed to each line on that new line. I turn it into a rope as opposed to leaving it as a string. And then I reset the current line. We do it again and again and again. And finally, after that loop is done, in case there is some additional characters that were put into that last line and there was no line-ending character, we might call the block one last time for any remaining characters there. But again, using Ruby, it ends up being relatively simple. Okay? So the basic code is already there. I uploaded it to RubyForge this morning, all right? And you can go to RubyForge, you can get 0.1. It's an alpha release. It works pretty well for what it does, but there's certainly a lot of more work to be done. And I'll show you some of the plans I have for it. And of course, if anybody else would like to get involved with it, they're certainly welcome to. Okay? There's also attached to the RubyForge project a rope announce mailing list, which you'll get announcements if you were interested in keeping up with that particular project. But again, my goal here is that the C++ programmers for the contest had this data structure in their back pocket. They just drop into their code and they were done. Okay? If you were using Ruby to do the programming contest, you would have to kind of basically wrap your own, create your own right then and there. So I think it's very beneficial to the Ruby community to have a lot of these basic data structures that are out there as RubyForge projects so that people can just drop them into their code and get the benefit of them without any additional effort. Now, again, because of the programming contest, there's been a lot of interest in ropes relatively recently. Here's a post by someone named John Miller. I don't suppose he's here. I've never met this person. No? Where he was talking about it. And he points out that one possible good use for ropes would be in ERB templates, because basically you're doing a lot of manipulations, replacing certain pieces with larger strings that you do through evaluating little bits of Ruby code. It would be a great place to actually employ ropes. He also says in the part in red that to use ropes only when string concatenation and slicing are the dominant operations you're doing on the data. And he says that those will be done in O of 1. I want to come back to that here in a moment, because what I showed you was not O of 1 for slicing, it was O of log n. And he kind of just contrasts the various kinds of applications that might benefit from using ropes versus those that might use traditional strings and get a better performance from them. All right? But let's come back to this issue of slicing. All right? Here's a slide I showed you previously where when I did a slice, I created another tree that tried to share as much as possible with the original tree. That's clearly an O log n operation. All right? And yet this person, John Miller, claimed that it could be done in O of 1. And I was actually made that slide, the previous slide, yesterday. And so in the interim, I started thinking about how would I possibly create a slice operation in constant time. All right? Basically, you can't descend the tree. So what can you do at the root level that would give you an O of 1 performance? Okay? So here's the rope once again. And basically, if you start thinking in terms of ropes and these nodes, basically you create another kind of node called maybe a partial node that says, hey, here's a rope, but don't look at the first 6 characters or the last 10 characters. Pretend that the first character in it is the 6th character, say. All right? And when you do that, you can create slices in O of 1 time. And you're sharing more data here. You're duplicating less. And so you're using less memory as well. So it does create opportunities to think of new kinds of nodes that you can add to the mix here to save you time and memory. Okay? Now, this is something I came up with in the last 24 hours. I actually have not implemented it yet in the library, but it seems like a good idea to do so. So kind of to summarize here, how do strings and ropes compare? So appending is much better on ropes than it is with strings. To retrieve a character at a particular index, either to retrieve it or alternatively to change it, strings have the great benefit right there, all right? Because the string can compute exactly where the character is using a simple multiplication, and boom, it can change it or retrieve it. With a rope, it's going to be a log n operations. That's where ropes are not quite as good as the strings. For slicing or substringing, again, with strings it'll be O of n. With the current implementation of my library, it's log n, but it could be made O of 1. And inserts can be made of O of 1 as well, because if you think about an insert, basically you're taking a slice for the front half of the original rope, a slice for the second half, which can now be made as O of 1, and then appending the 3 things together, which is also O of 1, constant time. And once you have the new slice substring, you can make inserts even faster as well. All right? If you go to the documentation for the SGI C++ library, they basically claim that ropes are actually a good choice as a normal or default representation for strings in a program. Some people would prefer to see them as opposed to the more traditional strings as far as the fundamental data structure in the programming language to hold strings of characters. And one thing I forgot to mention earlier is that Ruby not only uses strings to store textual data, Ruby uses strings to store binary data as well. If you load in a sound file or an image file, you don't have another kind of byte array or binary data type. Basically, you do that with strings as well. So whatever benefits you have with ropes for text data would apply to binary data as well. Okay? And he adds that the use of ropes minimizes the number of cases in which programming running times become intolerable due to unexpectedly long string inputs. Something to consider. I'm not sure whether I like the idea of completely replacing the default string representation with a rope, but it is something to think about, I think. As far as where to go from here with the library, well, clearly in some cases, these rope binary trees can become really out of whack, really unbalanced, depending on the operations you perform. So it might be a good idea to add rebalancing operations, either to be called manually or to keep some sort of measure about how out of balance things are, and when it reaches a particular threshold, then to do a rebalancing operation so you don't lose all the benefits you initially had. The string class provides lots of methods. Currently, the rope class provides some of the main ones that you would probably want to use, but not all of them, but they can be added. Add optimizations so that when you do a destructive operation, currently, because nodes can be shared, you have to then copy the nodes if you do a destructive operation. Perhaps we can keep track of which nodes are shared and which ones aren't, and when you're doing a destructive operation on a non-shared node, don't do the copy, and you can just do the operation in place. If you ever do a rope and double less than and then a single character, that's going to create a whole new level in your rope binary tree there, which can get really inefficient if you're doing a lot of those kinds of appending single characters onto the end of a rope. So there's probably a way to optimize that by maybe keeping a special buffer way at the top level for all those characters until they get enough of them to create another node and dropping into the tree someplace. All right? And of course, the optimization that I just discussed, making slicing and inserting constant time. Those would be good optimizations as well. One area where I'm very intimidated about how I would implement things, well, a couple areas. One is I don't know whether there'd be a huge benefit in using C as opposed to Ruby to implement the rope functionality, but something to consider. But regular expression support is a big one, all right? My understanding is that the library that Ruby uses to do regular expressions assumes that the strings are stored in the traditional string format, an array of bytes essentially, or an array of characters, all in one huge block. Getting that to work in this binary tree form, I'm not sure whether it would be easy or difficult, but my sense it would be somewhat difficult. I tried to do a little bit of monkey patching so that when you tried to do a regular expression match on a rope, it could maybe convert the rope to a string first to get it to work. But I found that when I tried to monkey patch using the literal regular expressions, either using the slash notation or the %r notation, that it wasn't calling a replacement method, which would check to see whether the right-hand side was a rope, and if so, call a particular method. Otherwise, it would call the method that it overrode. And I don't quite know what's going on there, but it seems that there's some optimization by the Ruby interpreter to handle those in the non-typical format. On the other hand, the green one, if I do that, then everything works just fine. So maybe someone out there knows why that happened.
They have bad accessing single characters and things like that. I can imagine with backtracking, it's going to...
Right. You know, you're absolutely right. In fact, I was thinking that I maybe had two choices as far as doing a simple implementation. One is to just raise an exception, all right? And if someone tries to do a regular expression operation, say, hey, this is not a good data structure to use regular expressions, but then allow someone to change a flag through a call saying, I know it's not efficient, but I want to do it anyway. And maybe at that point, I would convert it to a string and do the regular expression operation on the string instead. So I was thinking of maybe doing that, but you're right. There's probably a good point to be made as far as whether regular expressions are even appropriate for ropes.
Well, rather than throw an exception or something, just make it not work and provide a 2S method that if you call that explicitly, it works.
Right. Yeah. That might be a good alternative there, too. Was there another question there also? No? Yes.
Are you familiar with the piece table data structure?
I'm not.
Okay, it's very much like ropes. It's an old data structure. It was like developed at Park in the 70s, I think. But it's very much like ropes, except that it's essentially an array instead of a tree structure that mounts onto the backing store. The nice thing about the piece table was that you could plug multiple backing stores into it, so you could have a text file that was a read-only buffer, and you never did anything in there, and then you had an append-only buffer that you put all the new stuff in. And then you just created the piece data structures that mapped onto it. Really similar to ropes. Ropes look really cool because you get all of the tree structure advantages for logarithmic scaling. But it seems like there's a lot of cool stuff in the piece table engineering that could be folded into the ropes stuff.
Sure.
So that you could deal with these non-modified buffers and append only buffer.
Right. Just out of curiosity, I think I understood you correctly. So you would have the earlier part of the piece table be read-only, and the latter part of the very same piece table be your append buffer, or would those be separate structures altogether?
The way it was first used was you would open a file for editing, and it would be opened read-only, and then you'd create a second file, which was the append buffer. And when you saved the file, it would rewrite the file as one buffer.
Right.
So
yeah, that's the interesting thing with the ropes here. If you start making changes, it'll copy the little parts of the file out to make the changes into, and when the rope is, after a lot of editing has taken place, if you look at the rope, some nodes will be referring back to the file that have not been changed, but the ones that have been changed will be new kinds of nodes, like string nodes or partial string nodes, with the actual changes. So you'll actually have a mix in there, and then when you do the final write, you would rewrite everything sequentially. So I don't know whether that's the same or different.
It sounds pretty similar.
Okay.
So I started building a piece table implementation for last week's Ruby quiz, and I got about 90% done. So I'd love to come talk to you later. And
Definitely.
Please
do so.
Compare notes.
Sure. Are there other questions? Yes.
Does this have any specific implications for streaming or for simple playback of media files of all types? Normally we ping pong buffers to keep the context of the media that we're playing up to speed.
Right.
And I'm just wondering if this kind of tree structure would give us any special flexibility in dealing with those kinds of
Yeah, I guess I'm not too up on the intricate needs of streaming media. I mean, so it sounds like you have to have a buffer that, as you consume it, gets replaced with new stuff. I think ropes would work relatively well in that, especially if you had a nice large block size that was maybe some either the same size as your buffer or maybe some nice fraction of it, like a quarter of it or something like that.
In many cases, the block size has to be determined dynamically by the size of the pipe.
Right.
So,
and actually, the code here, if you look at it, if you go to the Ruby Forge project, you can actually download it, but you can specify the block size when you create a rope. So it's not hard-coded in any way. There's a default, which is 1K. But if you wanted to override that and make it larger or smaller, you definitely can. So perhaps. I don't know. I haven't thought through all of it, but it might be a good match. Are there other questions? Yeah?
How does this compare to skip lists?
Skip lists. When I was actually looking at that international ICFP programming contest, I was looking at the various options that people had there. And skip lists are basically, they work very much like binary trees as far as their running times go and things like that. Basically, you have a linked list, but you have another level above that which can skip over some intermediate nodes. And you can build another level on top of that which skips over some of those nodes. And basically, to traverse a skip list, you basically go up to the point where you can get as near as you want to your destination, and you drop back down. And the thing is, you can create your higher levels kind of stochastically based on some random values. You don't know exactly how many things you need to skip at each particular point. You can say, choose it somewhat randomly, and it kind of works out relatively nicely. So I basically think it would give you the same running time optimizations as you have with ropes. And furthermore, you could probably do the same lazy kind of evaluation as well. So there just might be an alternate implementation giving you pretty much the same functionality, I think. Until I actually tried to code it, I wouldn't know exactly if there were any differences that would kind of come out glaring at that point. All right. Other questions? Yeah.
So indexing into a string, isn't that just a specialized case of slice?
It is, except you actually want to return the character that's right there. All right. Someone says, what is the 12th character in the string? If we just do a slice, we can return them something which can give them access to it, but haven't given them direct access to it just yet. Then if they use that slice to get down and say, what is that character there, at that point we actually have to retrieve it and drop down through the tree. So there's a slight difference there. Other questions? All right. So in closing, by the way, this contest, which was very elaborate and very impressive, was created at the University of Freiburg in Germany. And it looks like they had spent roughly a year creating the structure for the contest. And they wrote a whole report after the fact, kind of describing their whole process in creating the contest and announcing who the winners were and how they approached their solutions and so forth. But they had a series of reflections here which I thought were kind of interesting. And let me kind of highlight certain key pieces of it here. It says many programmers don't have a lot of confidence in their favorite functional language. All right? Their first instinct was often to switch to a quote-unquote faster language like C. There was an IRC channel during the contest where people could exchange ideas, and they found that a lot of people started off trying to implement their solutions in a functional programming language. Once they hit that barrier, said, oh my gosh, my functional programming language is just too slow. I need to use C or something like that. All right? But the problem wasn't the language, but the algorithmic complexity, and a straightforward Haskell implementation using the right data structure, something called a data sequence there, would be fast enough to outperform by several orders of magnitude an optimized C implementation using a dumb data structure. All right? And the final little bit here is that so programmers should worry less about languages and more about good old complexity. And you probably won't hear it said in this particular conference, but some people claim that Ruby is slow. Ruby is not compiled, at least the current versions are not, and so on and so forth. But in fact, Ruby has many strengths. And with a nice complement of data structures, we can get past those various speed barriers as well. Now here is a list of the winners for the contest there. First prize went to a group out of Mountain View, California. They used C++. The second prize went to a group out of Cape Town, South Africa. They used Perl. And then there's a judge's prize, which was given to somebody or given to a team that showed some impressive ingenuity or something like that by the judges. And actually one person did that. He actually got the third best score as well, and he used a combination of OCaml and C++. And it would be great if Ruby were to show up on this list in a subsequent year. So if you have the inclination, when we have the 2008 contest, perhaps some of you will form up into teams and participate. We'll see what we can do. All right? So thank you. I was going to open up for questions. We're kind of roughly at the time limit right now, but if there are any other questions, I'd be happy to take them. And I'd also be curious, either we could do this through the announced mailing list for the Ruby Forge project or in here. Maybe there are other data structures that are incredibly useful, but that others haven't heard about. For example, ropes was brand new to me as of July. Okay? And I'm sure there are others out there as well that would be useful to know about and to create libraries for. Okay? So questions? Yes?
Another data structure I think you need to elaborate on some of the folk around Ruby Forge was circular list.
Uh-huh.
I haven't seen any other Ruby implementations yet. Probably be used as a standalone again.
Right.
It's been there for many years.
Uh-huh. Other questions or suggestions? Okay, and so here are a bunch of links, and I'll find a way to upload the presentation to a place where you can access it. But there are various links there that you might find useful. Thank you.